A silent, blinding flash of light, followed by a shaking rumble of noise. We've all seen it. But if you look closely, the timing is a physical reality. This is a thunderstorm, a weather phenomenon defined by electrostatic discharge. Within this single event, we are witnessing a massive shift in energy. Now, why does the flash happen instantly, while the loud sound that follows, which we call thunder, causes a delay? Well, the answer lies in the physics of speed. Light travels much faster than sound, 1,000,000 times faster, in fact. Because lightning travels at the speed of light, it reaches your eyes before the noise can travel the distance. The flash is instant. The thunder takes longer to travel. High above us, inside the swirling chaos of a thundercloud, a massive buildup of electricity is happening. It's as if the sky is acting as a giant battery being charged, with a powerful electric field forming between the top and the base of the cloud. This process of charge separation creates an accumulation of electric charges that just wants to break through. But for a while, the air itself acts as a barrier. Because of the insulating properties of the air, the electricity cannot simply jump the gap. It's held back, tension building up until the pressure is the only thing that can break it. Now, this is not a rare event. Across our planet, lightning strikes occur approximately 3 billion times a year globally. That's an incredible scale of energy, roughly 100 times per second. Every single second, 100 bolts of plasma are fighting to find a path through the insulating air to the ground. Now, let's look at how this energy actually descends. It isn't a single straight line, it's a surge. Most of the time, we see what we call cloud to ground, or CG lightning, where the charge descends from the sky to the ground. But the atmosphere is far more versatile. Energy can jump between clouds, known as cloud to cloud, or CC lightning, or even move within a single storm cell. This is intracloud, or icy lightning. When we talk about the specific look of the bolt, we see a variety of forms. Some are the jagged, branching paths of fork lightning, while others appear as a broad, shimmering wall of light. That's sheet lightning. There are even a few rare, mysterious occurrences of ball lightning, which manifests as a luminous sphere. But the most critical part of the process is the descent. The electricity doesn't just fall. It's a blind, jagged search for the ground. It moves in pulses, creating what we call a stepped leader, which probes the atmosphere in increments of roughly 50 meters, branching out like an electrical root system until it finally finds a path of least resistance to reach the Earth. But the sky isn't the only actor here. As the stepped leader descends, the ground actually reaches back. This is where we encounter the upward streamer. This interaction is what gives the lightning bolt's appearance. While most bolts are bright white or yellowish white, the color of lightning depends on the temperature and the gases in the air when it occurs. Some strikes can even be blue, purple, red, or even green. It's a weird atmospheric chemistry experiment happening at a scale that is absolutely terrifying. Now, does the ground really want to connect with the cloud? It's like an invisible handshake up until the moment they meet. Everything changes the moment that invisible bridge is completed. This is the return stroke. This is the part we actually see as a blinding flash of plasma. It's an explosion of energy that happens so fast, the temperature inside the lightning channel varies during its 50 microsecond existence. 50 microseconds. That's a window of time so small, it's almost impossible to imagine. If you blink your eye once, a single bolt of lightning has already lived its entire life cycle up and down the channel. In terms of speed, we are comparing two completely different worlds. Light travels at nearly 300,000 kilometers per second, while sound is a slow crawl by comparison. This gap in speed is the physical reason why the flash arrives first, and the sound is left behind, struggling to catch up. It's not a chance occurrence, it's a mathematical certainty of the atmosphere. It's almost surreal that something so brief is so powerful. We're talking about a single bolt carrying between 1 to 10 billion joules of energy. To put that into a perspective you can actually see, that's enough energy to keep a single electric bulb lit for about 3 months. Just think about that. A fraction of a second of atmospheric chaos provides more power than a home appliance uses in an entire season. It's a staggering amount of force concentrated into a thin line of plasma, proving that the storm doesn't need time to be devastating. It just needs one perfect connection. Let's talk about the heat. When that bolt hits, it doesn't just light up the sky, it heats up the air around it very quickly. This sudden increase in temperature and pressure creates a massive, rapid expansion of the air. Since the 20th century, scientists have agreed that thunder begins with a shock wave in the air, caused by the sudden thermal expansion of plasma in the lightning channel. Think about the scale of this energy. The main lightning channel can reach temperatures of around 30,000 degrees Celsius or 54,000 degrees Fahrenheit. To put that in perspective, lightning is hotter than the surface of the sun, about 5 times hotter in fact. What happens when air is heated to 50,000 degrees Fahrenheit so instantly? It doesn't just move, it explodes. This shockwave created by lightning causes the big booming sound known as thunder. That thunderous rumbling sound is simply the atmosphere's reaction to the heat. It's a sonic boom on a planetary scale, where the rapid expansion of air transforms a blinding flash of plasma into a loud boom. Have you ever wondered why some thunder sounds like a low growl? It all comes down to the distance and the nature of the lightning. When you are close to the strike, you hear a sudden, loud crack, a snap, or even a sharp crack. It's a violent, sudden burst of energy that can be loud enough to shake the ground. But as the sound waves travel further away, they bounce and echo, transforming into a long, low rumble. The sound changes because the air and the distance from the source of the shockwave actually shape the sound we hear. It's a fascinating puzzle of geometry and physics where a jagged line of light is converted into a rhythmic thumping of the air. It's a common misconception that a lightning strike is an automatic death sentence. In reality, approximately 90% of lightning strike victims survive, but the physical toll is immense. The electric current can break the heart's electrical rhythm, leading to cardiac arrest, while other victims suffer from seizures, respiratory arrest, or even permanent brain damage, coma, and paralysis. If you are within 30 feet of the strike point, the strike's blast wave is equivalent to a 5-kilogram TNT explosion. That pressure can rupture your eardrums and cause permanent hearing loss, and the scorching heat and electric current can damage your eyes. One of the most hauntingly beautiful marks of this power is the Lichtenberg figure. These are tree-like, branching scar patterns on the skin, caused when the electricity bursts the red blood cells in the capillaries of the epidermis. In a world where we think we are in control, the storm doesn't follow a rule book. It just follows the physics. That's why the saying that lightning never strikes twice is a myth. In an open field or a tree line, charges accumulate in ways that make it possible for the same spot to be hit many times. To stay safe, you must avoid standing under a tree, near a pool, or in an open field. You are safest indoors, under a building, or in a vehicle. Most people see a single bolt of lightning and think it's one event, but it's often a series of rapid-fire pulses. Once the conductive path is established, the current is reinforced by dart leaders, darting through the same channel to reinforce the same strike. It's this flickering effect that makes a bolt look like it's pulsing. Now, from what we can tell, this sight is more than just a wonder. For some, it's a source of deep, irrational fear. There is a specific term for this, kuranophobia. While brontophobia is the fear of thunder, kuranophobia is the irrational fear of lightning itself. But it's fascinating to see how our understanding of these storms has evolved. The scientific study of thunder, known as brontology, has a long history of guesswork. Long ago, ancient Greek philosophers like Anaximander and Aristotle attributed thunder to wind striking clouds. Democritus, however, a different Greek philosopher, believed the movement of air within clouds was the cause. The Roman philosopher Lucretius believed thunder was caused by the sound of hail colliding within clouds. Meanwhile, our language even carries these ancient echoes. The modern English word thunder comes from the Old English word thunor, which shares a root with the name of the Nordic god Thor and derived from the Old Norse word for thunder. All of this is sounded out in the shared Proto-Indo-European root, stonor, also found in Gaulish Tyrannus. From the colliding ice crystals in a swirling cloud to the final bone-shaking rumble of thunder, the storm is a masterclass in physics. We've seen how the sky becomes a battery, how a stepped leader blindly searches for the ground, and type, object, properties, result, type, string, required, result.